I've always found it strange that the most extreme objects in the universe are also the easiest to describe. A teaspoon of neutron star material weighs about 6 billion tons. That's not a metaphor or an approximation dressed up for effect. It's simply what happens when you compress matter beyond any familiar limit. Neutron stars are the collapsed cores of dead stars, objects roughly the size of a city, but containing more mass than our Sun. They're smooth, dense, impossibly compact, and they exist scattered throughout our galaxy, spinning quietly in the darkness. You're listening to the Drowsy Astronaut, and this is going to be a slow journey through one of the strangest classes of objects we've ever found. There's no rush here, no deadline, just a long and gentle look at something truly unusual. If you're listening from bed, from a quiet room somewhere, or from the other side of the world as night settles in, feel free to let me know in the comments. I'm always curious where these stories end up. Neutron stars are what remain after certain massive stars exhaust their fuel and collapse. The outer layers explode outward in a supernova, but the core, no longer supported by the heat of fusion, falls inward under its own gravity. In less than a second, a sphere of matter larger than Earth compresses into something about 20 kilometers across. What's left behind is an object so dense that the rules governing normal matter no longer apply. Atoms, as we know them, cannot exist there. The pressure is too great, the gravity too strong. The density of a neutron star is difficult to grasp, not because the numbers are complicated, but because they describe a state of matter we have no direct experience with. On Earth, the densest naturally occurring element is osmium, at around 20 grams per cubic centimeter. Water, by comparison, is 1 gram per cubic centimeter. Neutron star material in its outer crust starts at around 1 million grams per cubic centimeter. Deeper inside, that number climbs into the hundreds of millions. A single teaspoon, just 5 milliliters, of matter from the interior of a neutron star would weigh somewhere between 5 and 6 billion tons. If you could somehow lift that teaspoon, which you couldn't, and bring it to Earth, which you shouldn't, it would punch through the ground as if the planet were made of paper. Gravity would pull it downward with such force that nothing could stop it. It would fall toward the center of the Earth, oscillating back and forth through the core until friction, over a long time, brought it to rest. Of course, this is all deeply hypothetical. Neutron star material cannot exist outside the intense gravitational environment that creates it. Remove that pressure, and the matter would explode outward, violently, instantly. But the thought experiment is useful because it makes the density feel a little more real. Neutron stars are not large. 20 kilometers across is about the size of a city, Manhattan perhaps, or central London. You could, in theory, walk across the diameter of a neutron star in a few hours, though the gravity would make that impossible in ways we'll get to. Despite their size, neutron stars are more massive than the Sun, which is almost 1.5 million kilometers across. This combination, extreme mass compressed into extreme smallness, creates an environment unlike anything else we've encountered. The surface gravity is around 200 billion times stronger than Earth's. Light itself bends noticeably around them. Time, relative to an outside observer, runs slower near their surfaces. They emit radiation, often in steady pulses, as they rotate. These pulses were first detected in the 1960s, and for a brief time, astronomers genuinely considered the possibility that they were artificial signals, beacons from some distant intelligence. The regularity was too precise, the timing too exact. But as more were found, and the physics became clearer, the truth emerged. Neutron stars are natural objects, and their precision comes not from design, but from the fundamental physics of rotation and conservation of angular momentum. When a star collapses, it spins faster, just as a figure skater spins faster when pulling their arms inward. Some neutron stars rotate hundreds of times per second. The fastest known pulsar, catalogued as PSR J17482446 AD, spins at roughly 716 rotations per second. Imagine a sphere more massive than the Sun, 20 kilometers across, rotating more than 700 times every second. The equator of that star is moving at a significant fraction of the speed of light, and yet the structure holds. The neutron star does not fly apart, does not deform beyond a slight equatorial bulge. Gravity keeps it intact, binds it together with a force nothing in our everyday world can match. The material is not just dense, it's also extraordinarily smooth. The surface of a neutron star is the flattest naturally occurring surface in the universe. Mountains, if they exist at all, are no more than a few millimeters tall. Any irregularity larger than that would be crushed flat by gravity within moments. The crust, made mostly of iron nuclei packed into a crystalline lattice, is thought to be the strongest material anywhere. It's millions of times stronger than steel, but also brittle under the right conditions. When it cracks, the release of energy can be detected from thousands of light years away. Beneath the crust, the structure becomes stranger. The nuclei begin to deform, pressed into shapes that don't exist anywhere else. Rods, sheets, tubes, structures that physicists have named, somewhat playfully, nuclear pasta. Deeper still, the nuclei dissolve entirely, and matter exists as a sea of neutrons, with a scattering of protons and electrons moving through it. This neutron fluid is thought to be a superfluid, meaning it flows without viscosity, without friction. And the protons, under these conditions, may form a superconductor, carrying current without resistance. These are not speculative ideas pulled from science fiction. These are serious predictions from quantum physics, applied to conditions we can observe, but not yet fully replicate or confirm. The core, the very center of a neutron star, remains uncertain. We don't know exactly what happens there. The pressures and densities exceed anything we can create in a laboratory, and the physics governing matter at that scale is still debated. Some models suggest that quarks, the particles that make up neutrons and protons, might break free and exist independently, forming what's called quark matter. Other models propose different states, different configurations. The truth is, we're not sure, and that uncertainty, rather than being frustrating, is part of what makes neutron stars so compelling. They're small enough to study as whole objects, yet extreme enough to push the boundaries of known physics. They sit at the intersection of quantum mechanics, which governs the very small, and general relativity, which governs the very massive. Both frameworks apply, both are necessary, and in some regions, they overlap in ways we're still working to understand. Neutron stars are natural laboratories, testing our theories in conditions we could never design ourselves. There are thought to be around 100 million neutron stars in our galaxy alone, though we've only detected a few thousand. Most are invisible, or at least very faint, emitting radiation outside the range we typically observe. or pointing their beams of light away from us. The ones we do see, the pulsars, are visible because their rotation sweeps a beam of radiation across our line of sight, like a lighthouse. If the beam doesn't point toward Earth, we don't see it. So for every neutron star we've catalogued, there are likely many thousands we haven't. They exist in a variety of states. Some are isolated, drifting silently through space, cooling slowly over billions of years. Others orbit companion stars, pulling matter from them, feeding on their outer layers in a process that reheats the neutron star and changes its behavior. Some are paired with other neutron stars, locked in binary orbits that gradually decay as they lose energy to gravitational waves. And a few, a rare subset, possess magnetic fields so strong that they distort the vacuum of space itself. These are called magnetars, and their fields are trillions of times stronger than anything we can produce on Earth. But before we go further into their behavior, their histories, or their futures, it's worth pausing on that original fact, the one that brings most people to neutron stars in the first place. A teaspoon of this material weighs 6 billion tons, not because it's made of something inherently heavy, but because the space between particles, the empty volume that makes up most of normal matter, has been removed. Neutrons are packed together as tightly as they can be without collapsing further into a black hole. It's matter at the edge of what matter can be. And that edge is where we'll spend the rest of this journey, looking at what happens when stars die in a particular way, when mass and gravity and quantum physics conspire to create something small, dense, and stranger than almost anything else in the cosmos. A neutron star is, at most, about 20 kilometers across. Some are smaller, closer to 10 kilometers in diameter. For scale, that's less than the width of many metropolitan areas. You could fit a neutron star comfortably within the borders of a large city. And yet, despite this compactness, a typical neutron star contains between 1.4 and 2 times the mass of the Sun. The Sun, for reference, is nearly 1.5 million kilometers in diameter. If you placed the Sun and a neutron star side by side, the size difference would be absurd, almost comical. But the neutron star would be more massive. This is the fundamental paradox of neutron stars. They're extraordinarily small and extraordinarily heavy. There's no familiar comparison that quite captures it. Imagine trying to fit all the mass of a mountain into a grain of sand, then multiplying that disparity by a factor of millions. Even that doesn't do it justice. The Sun is large and massive, but it's also diffuse. Its average density is only about 1.4 grams per cubic centimeter, slightly denser than water. A neutron star, compressed by gravity into a sphere barely wider than a city, achieves densities that make the Sun seem almost hollow by comparison. The mass of a neutron star is constrained by physics. If the core of a collapsing star is too light, it becomes a white dwarf instead, supported by electron degeneracy pressure rather than neutron degeneracy. If it's too heavy, gravity wins entirely, and the collapse continues past the neutron star stage, forming a black hole. The boundary, known as the Tolman-Oppenheimer-Volkoff limit, is somewhere between 2 and 3 solar masses, though the exact value depends on the equation of state of neutron matter, which is still uncertain. Most neutron stars we've measured fall between 1.4 and 2 solar masses, clustered in a relatively narrow range. But mass alone doesn't define them. It's the combination of mass and size that creates the extreme conditions we associate with neutron stars. Gravity at the surface is immense. on the order of 200 billion times Earth's gravity. If you were standing on the surface of a neutron star, which you couldn't, you would be flattened instantly into a layer of atoms less than a micrometer thick. Every atom in your body would be crushed downward with a force incomprehensible to human experience. Even light struggles to escape. Photons climbing out of the gravitational well lose energy, shifting toward the red end of the spectrum in a process called gravitational redshift. This intense gravity warps space-time around the neutron star in measurable ways. Light doesn't travel in straight lines near these objects. It curves, bending around the star as it passes. If you were somehow orbiting close to a neutron star and looking at its surface, you could see more than half of it at once. The light from the far side would bend around the edges and reach your eyes. This lensing effect allows astronomers to observe regions of the surface that would otherwise be hidden, providing clues about the star's shape, its hotspots, and the structure of its magnetic field. The shape of a neutron star is not perfectly spherical. Rotation causes a slight equatorial bulge, just as it does with Earth, but the effect is more pronounced for fast-spinning neutron stars. Still, the deformation is small, typically no more than a few percent. Gravity is strong enough to resist even the centrifugal forces of rotation, measured in hundreds of times per second. The star remains nearly round, nearly smooth, held together by forces that dominate every other consideration. Because of their small size and high mass, neutron stars have escape velocities that approach a significant fraction of the speed of light. To leave the surface of a neutron star, you would need to be traveling at around half the speed of light, depending on the star's exact mass and radius. For comparison, Earth's escape velocity is about 11 kilometers per second. Neutron stars operate in a regime where relativistic effects, the strange behaviors predicted by Einstein's theory of general relativity, are not minor corrections but dominant features of reality. Time itself runs slower near the surface of a neutron star than it does far away in open space. This is gravitational time dilation, a consequence of curved spacetime. A clock on the surface of a neutron star would tick measurably slower than a clock held by an observer far from any gravitational source. The difference isn't dramatic on human timescales, but it's real and it's measurable. Light emitted from the surface carries the signature of this time dilation in its spectrum, allowing astronomers to test general relativity in one of the most extreme environments available. The relationship between size and mass also determines the internal structure of a neutron star. The more massive the star, the smaller it becomes. This seems counterintuitive, but it's a consequence of how gravity and pressure interact. As you add mass to a neutron star, gravity compresses it further, shrinking its radius. There's a point, still debated, where adding more mass doesn't increase the size at all. It just compresses the star into an ever smaller volume until the collapse can no longer be stopped and a black hole forms. This inverse relationship between mass and radius is unique to degenerate objects like neutron stars and white dwarfs. Neutron stars aren't all identical. Their masses vary, their rotation rates vary, their magnetic fields vary, and their temperatures vary. Some are young, still glowing from the heat of their violent formation, with surface temperatures reaching several million degrees. Others are old, cooled over billions of years to temperatures closer to a few 100,000 degrees. Still extraordinarily hot by any normal measure, but faint and difficult to detect. The cooling process is slow, governed by the emission of neutrinos from the interior and photons from the surface, and it gives astronomers a way to estimate the age of isolated neutron stars. There are neutron stars that orbit other stars, locked in binary systems where matter flows from a companion onto the neutron star's surface. This accretion heats the neutron star back up, reversing the cooling process and creating bursts of X-rays as the infalling material crashes into the surface at a significant fraction of light speed. The impacts release more energy in a fraction of a second than the sun emits in days. And yet, from a distance, these systems can appear almost steady, pulsing gently as the neutron star rotates and the hotspots on its surface come in and out of view. The size of a neutron star also determines the strength of its gravity at a given distance. Because they're so small, you can get very close to the center of mass before encountering the surface. Orbits near a neutron star are fast and tight. A particle orbiting just above the surface would complete a circuit in a fraction of a millisecond. For comparison, the International Space Station orbits Earth roughly every 90 minutes. The difference in orbital dynamics is vast, a reflection of how concentrated mass becomes when compressed into such a small volume. When two neutron stars orbit each other, their mutual gravity creates ripples in space-time itself, gravitational waves that propagate outward at the speed of light. These waves carry energy away from the system, causing the orbit to slowly decay. Over millions or billions of years, the two neutron stars spiral closer and closer together until, eventually, they merge. The collision releases a tremendous amount of energy, briefly outshining entire galaxies, and produces heavy elements like gold and platinum in quantities that dwarf any other known process. But we'll return to that later. For now, it's enough to understand that neutron stars occupy a strange place in the universe. They're too small to see directly, even with our most powerful telescopes. We know their size mostly from theory, from models of how matter behaves under extreme pressure, and from indirect observations of their brightness, their spectra, and the way their gravity affects nearby objects. The actual surface, that impossibly smooth sphere of compressed matter, remains hidden from direct view, inferred rather than observed. Yet their mass is unmistakable. We measure it through their gravitational effects on companion stars, through the precision timing of their pulses, and through the gravitational waves they emit. Mass leaves signatures everywhere, in the motion of objects, in the bending of light, in the fabric of space-time itself. And neutron stars, despite their size, have mass enough to make themselves known across thousands of light years. They are proof, in a way, that size and influence are not the same thing. That something small can still warp the space around it, can still anchor orbits, can still emit signals powerful enough to cross the galaxy. And that density, the simple measure of how much mass occupies how much space, can become extreme enough to challenge our intuitions and push the boundaries of what matter can be. Neutron stars are born in violence, but what they leave behind is silence. They form during the collapse of massive stars, the final moments of stellar lives that have lasted millions of years. When a star with a core mass between about 1.4 and 3 times the mass of the Sun exhausts its nuclear fuel, there's nothing left to hold it up. The outward pressure from fusion, which has supported the star against gravity for its entire life, suddenly vanishes. And in the absence of that pressure, gravity acts unopposed. The collapse happens fast, The core of the star, roughly the size of Earth, falls inward and compresses to a sphere, 20 kilometers across in less than a second. The outer layers, no longer supported, fall inward as well, but they encounter the rebounding shock wave generated when the core reaches neutron degeneracy and halts its collapse. That shock wave, amplified by a flood of neutrinos streaming outward from the newborn neutron star, blows the outer layers into space at speeds of tens of thousands of kilometers per second. This is a supernova, one of the brightest events in the universe. For a few weeks, the exploding star can outshine its entire host galaxy. The light is visible across millions, even billions, of light years. But the brightness fades, and what remains at the center, hidden within the expanding cloud of gas and dust, is the neutron star. It's hot, spinning rapidly, and surrounded by debris, but it's stable. The collapse has stopped. The core has found a new equilibrium, supported now not by heat or electron pressure, but by neutron degeneracy pressure, a quantum mechanical effect that prevents neutrons from being squeezed into the same space. Not all stars become neutron stars. Stars, less than about 8 times the mass of the Sun, don't have enough mass in their cores to trigger a supernova. They end their lives more gently, shedding their outer layers as planetary nebulae, and leaving behind white dwarfs, objects supported by electron degeneracy rather than neutron degeneracy. Stars much more massive than about 20 or 30 solar masses may collapse directly into black holes, bypassing the neutron star stage entirely. Neutron stars then come from a specific range of stellar masses, a narrow window in the life cycle of stars. The exact mechanism of supernova explosions is still debated. We know the general outline: the collapse, the rebound, the explosion, but the details are complex. Computer simulations of core collapse often struggle to produce explosions unless certain conditions are met. The role of neutrinos, the behavior of the shock wave, the influence of rotation and magnetic fields, all of these factors matter, and all of them are difficult to model. Real supernovae, observed in distant galaxies, don't always match the predictions. Some are brighter than expected, some dimmer, some leave neutron stars behind, and some apparently don't. What we do know is that the transition from normal matter to neutron matter happens in an instant. During the collapse, as densities climb beyond the point where atomic nuclei can exist as separate entities, protons and electrons are forced together. The electromagnetic repulsion that normally keeps them apart is overcome by the sheer pressure of gravity. Protons and electrons combine, forming neutrons and releasing neutrinos in the process. This neutronization is the key step, the transformation that allows matter to compress far beyond the density of atomic nuclei. The neutrinos, nearly massless particles that barely interact with anything, stream outward from the collapsing core in vast numbers. In the first few seconds after a neutron star forms, it emits more energy in neutrinos than the Sun will emit in photons over its entire 10 billion year lifetime. Most of these neutrinos pass through the outer layers of the star without interacting at all, escaping into space, carrying information about the core that we can, in principle, detect. The 1987 supernova in the Large Magellanic Cloud, designated SN 1987A, was detected not just in light, but also in neutrinos, marking the first time we observed the birth of a neutron star through multiple channels. Rotation plays a crucial role in the birth of neutron stars. The original star, before collapse, was rotating slowly, taking days or weeks to complete a single turn. But as the core collapses and its radius shrinks, conservation of angular momentum forces it to spin faster. A core that was rotating once every few days might, after collapse, rotate several times per second. Some neutron stars are born spinning even faster, particularly if the original star was rotating rapidly, or if the core fragmented and transferred angular momentum during the collapse. Magnetic fields also intensify during collapse. The original star had a magnetic field, relatively weak compared to what comes next. But as the core shrinks, the magnetic field lines are compressed and amplified, sometimes by factors of trillions. The result is a neutron star with a magnetic field far stronger than anything found elsewhere in nature. In some cases, if conditions are right, the field can reach strengths that classify the neutron star as a magnetar, but that's a topic we'll explore more fully later. The supernova itself, the explosion, does more than just reveal the neutron star. It also disperses the elements created during the star's lifetime back into space. Carbon, oxygen, silicon, iron, all the elements forged in the star's core during millions of years of fusion are scattered across light years, mixing with the interstellar medium, enriching the gas clouds that will eventually form new stars and planets. The neutron star, by contrast, keeps almost nothing. It's made almost entirely of neutrons, with a thin crust of iron and heavier nuclei. The complexity of the original star, its layers of different elements, its history of fusion, all of that is erased. What's left is something simpler, in a way, but also far stranger. A sphere of neutrons, bound by gravity, spinning in space, cooling slowly, emitting radiation. It's no longer a star in the traditional sense. It's not fusing elements, not generating energy through nuclear reactions in its core. It's a remnant, a fossil of a process that ended violently, but left behind something remarkably stable. Some neutron stars are born in binary systems, where the original massive star had a companion. If the companion survives the supernova, which it often does, the neutron star remains in orbit around it. This can lead to complex interactions later. As we'll see, other neutron stars are born alone, either because their progenitor star was isolated or because the supernova explosion was asymmetric enough to kick the neutron star out of its original system, sending it drifting through the galaxy at speeds of hundreds of kilometers per second. The kick, if it happens, comes from asymmetries in the supernova explosion itself. If the explosion is not perfectly symmetric, if more material is ejected in one direction than another, the neutron star recoils in the opposite direction, like a rocket. Some neutron stars have been found moving at velocities exceeding 1,000 kilometers per second, fast enough to escape the gravitational pull of the galaxy entirely, though most remain bound and simply wander through the Milky Way's disk and halo. The birth of a neutron star is, in many ways, the end of one story and the beginning of another. The massive star that spent millions of years fusing hydrogen into helium, helium into carbon, carbon into heavier elements is gone. What remains is something that will exist, largely unchanged, for billions or even trillions of years. The neutron star will cool, it will slow its rotation, it may interact with other objects, but it will not evolve in the way stars do. It's reached a kind of endpoint, a stable configuration that, barring external interference, will persist far longer than the star that created it. And yet, despite their stability, neutron stars are not quiet. They pulse, they emit radiation, they generate magnetic fields that shape the space around them. They're small, but they make themselves known. And the process that created them, the supernova, is one of the most energetic events in the universe. A bright and unmistakable signal that somewhere, a massive star has died, and something new, something dense and strange has been born in its place. The inside of a neutron star is layered, structured, and unlike anything we can directly study on Earth. From the surface down to the core, matter exists in states that change with depth. Each layer governed by different physics, different pressures, different arrangements of particles. Understanding this structure requires combining observations with theory, using what we know about nuclear physics and quantum mechanics to infer what must be happening deep inside an object we can never open or sample. The outermost layer, the atmosphere, is extraordinarily thin, just a few centimeters deep. It's made of ionized hydrogen, or perhaps carbon, depending on the neutron star's history and temperature. Despite its thinness, this atmosphere is where most of the star's thermal radiation escapes, and it shapes the spectrum of light we observe. The temperature here can reach 1,000,000 degrees or more, hot enough that the atoms are completely ionized, stripped of their electrons. But compared to the interior, this layer is almost negligibly thin, a skin stretched over something far denser. Beneath the atmosphere lies the outer crust, a solid shell roughly a kilometer thick. Here, the density is lower than in the deeper interior, but still immense by terrestrial standards. The matter is arranged in a crystalline lattice of atomic nuclei, mostly iron and similar heavy elements, immersed in a sea of free electrons. The nuclei are packed far more tightly than in normal matter, but they still exist as discrete entities, separated by electrons that move freely through the lattice. This is the strongest material in the universe, millions of times harder than steel, yet brittle under certain conditions. As you descend deeper into the crust, the density increases, and the nuclei become more neutron-rich. Under normal conditions, nuclei with too many neutrons are unstable, decaying quickly. But here, the immense pressure stabilizes them. The nuclei grow larger, heavier, more distorted. Eventually, at densities around 1,000,000 billion grams per cubic centimeter, the nuclei begin to touch each other. The spaces between them vanish, and the structure changes. This is the transition to the inner crust, a region where the nuclei deform and merge into shapes that don't exist anywhere else. Physicists call these structures nuclear pasta, because the shapes resemble different types of pasta. At lower densities, you get spherical nuclei, like gnocchi. As density increases, the nuclei stretch into rods, like spaghetti. Higher still, they flatten into sheets, like lasagna. Then the structure inverts, forming tubes and bubbles. These shapes are predicted by simulations of nuclear matter under extreme pressure, but we've never observed them directly. They exist, if they exist, only in the inner crusts of neutron stars. Below the crust lies the outer core, where atomic nuclei dissolve entirely. The density here exceeds the density of an atomic nucleus, around 200 million billion grams per cubic centimeter. And matter exists as a fluid of neutrons, with a small fraction of protons and electrons mixed in. This neutron fluid is thought to be a superfluid, a quantum state where the particles flow without viscosity, without friction. Superfluidity is observed in laboratories on Earth, in liquid helium cooled to near absolute zero. But in neutron stars, it occurs at temperatures of millions of degrees, sustained by the extreme density and quantum pressure. The protons, present in much smaller numbers, may form a superconductor, allowing electric current to flow without resistance. Superconductivity, like superfluidity, is a quantum phenomenon, normally observed only at very low temperatures. But again, the conditions inside a neutron star are so extreme that the usual rules don't apply. The combination of superfluid neutrons and superconducting protons has implications for the star's magnetic field, its cooling rate, and the way it responds to rotation. The outer core makes up the majority of the neutron star's volume and mass. It's a relatively well-understood region, at least compared to what lies below. The physics governing neutron superfluids is complex, but it's based on principles we can test, at least in part, in laboratories. The equations of state, which describe how pressure relates to density, are constrained by observations of neutron star masses and radii, and by measurements of how matter behaves in particle accelerators. We're fairly confident about the general picture, even if many details remain uncertain. But then there's the inner core, the center of the neutron star, where the density climbs higher still and our certainty fades. At densities several times that of a normal atomic nucleus, we don't know exactly what happens. The neutrons might remain as neutrons, packed as tightly as quantum mechanics allows, or they might break apart into their constituent quarks, forming a quark-gluon plasma similar to what existed in the first moments after the Big Bang. Or something else entirely might occur, some phase of matter we haven't yet predicted. Different models of the equation of state predict different outcomes. Some suggest that the core remains neutron-rich, perhaps with exotic particles like hyperons or kaons mixed in. Others suggest a transition to quark matter, where up, down, and strange quarks exist freely rather than being confined inside neutrons and protons. Still others propose hybrid stars, with a quark core surrounded by a neutron mantle. The truth is, we don't know. The physics at these densities is uncertain, and the observations we have, precise as they are, don't yet rule out enough possibilities. Neutron stars are, in a sense, natural experiments in nuclear physics. They compress matter to densities we can't achieve on Earth, not even in the most powerful particle colliders. They test the limits of quantum chromodynamics, the theory that describes the strong nuclear force, in regimes where that theory is difficult to calculate. Every observation of a neutron star's mass, radius, or behavior provides a constraint on the equation of state, narrowing the possibilities, ruling out models that don't match reality. Recent observations have begun to tighten these constraints. Measurements of neutron star radii, derived from X-ray observations of hotspots on their surfaces, suggest that the equation of state is relatively stiff, meaning that matter resists compression more than some models predicted. Gravitational wave detections from merging neutron stars provide additional information, because the way the stars deform before merging depends on how compressible they are. Each new observation adds a piece to the puzzle, slowly building a clearer picture of what's inside. The interior structure also affects how neutron stars cool. Heat generated during the supernova slowly escapes over millions of years, carried away by neutrinos from the interior and photons from the surface. The cooling rate depends on what's inside. Superfluids cool differently than normal fluids. Quark matter, if it exists, might cool faster or slower, depending on the details. By observing the temperatures of neutron stars of different ages, astronomers can test models of the interior, comparing predictions to reality. Some neutron stars cool faster than expected, others slower. The variations hint at differences in composition, in internal structure, perhaps in the presence or absence of exotic matter. A neutron star with a quark core might cool differently than one without. A star with a strong magnetic field might transfer heat differently than one with a weak field. The cooling curves, plotted over millions of years, are clues to what's hidden beneath the surface. The layered structure of a neutron star also influences its dynamics. The superfluid interior doesn't rotate at the same rate as the solid crust. When the crust slows down due to magnetic braking or other processes, the superfluid continues rotating at its original speed, at least for a while. Eventually, the two regions couple, and the superfluid transfers angular momentum to the crust in sudden jumps, called glitches. These glitches are observed in pulsars, sudden increases in rotation rate that occur irregularly, unpredictably, and they provide direct evidence of the superfluid interior. The interior of a neutron star is, in many ways, the least accessible part of the universe. We can't visit it, we can't sample it, we can barely even observe it directly. What we know comes from inference, from combining theory with observation, from building models and testing them against reality. And yet, despite the difficulty, we've learned a great deal. We know the general structure, the layers, the transitions. We know that matter behaves in ways that challenge our understanding, that push the boundaries of nuclear physics and quantum mechanics. What we don't know is just as interesting. The exact state of the core, the presence or absence of quark matter, the details of superfluidity under these conditions, all of these remain open questions. And every neutron star we observe, every measurement we make, brings us a little closer to answers. Not quickly, not easily, but steadily. Over decades of observation and theory, the picture sharpens. The interior slowly reveals itself, not through direct inspection, but through the careful accumulation of clues. Neutron stars spin. Some spin slowly, once every few seconds. Others spin hundreds of times per second, rotating so fast that their equators move at a substantial fraction of the speed of light. This rotation, combined with the emission of beams of radiation from the star's magnetic poles, creates one of the most distinctive phenomena in astronomy, the pulsar. The name is short for pulsating star, though neutron stars don't actually pulsate. They emit steady beams of radiation, and as they rotate, those beams sweep across space like the light from a lighthouse. If one of the beams points toward Earth, we see a pulse. If it doesn't, we see nothing. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student working with Anthony Hewish at Cambridge. She noticed a strange signal in the data from a radio telescope, a series of pulses arriving with extraordinary regularity, every 1.3 seconds. At first, the signal was so precise that the team briefly considered the possibility that it was artificial, a beacon from an extraterrestrial civilization. They even jokingly labeled it LGM, one for little green men. But as more pulsars were found, each with different periods, it became clear that these were natural objects, and the leading explanation soon emerged: rapidly rotating neutron stars. The regularity of pulsars is remarkable. The best pulsars keep time as accurately as atomic clocks, their pulses arriving with such precision that deviations can be measured in microseconds over years. This stability comes from the physics of rotation. A neutron star, once formed, has no internal processes that would speed it up or slow it down significantly. Aside from the gradual loss of rotational energy through magnetic braking, the rotation period is determined by the conservation of angular momentum from the original stellar core, and it changes only slowly, predictably over long timescales. The pulses themselves come from radiation emitted along the magnetic poles of the neutron star. The magnetic field, intensified during the star's formation, is not aligned with the rotation axis. As the star spins, the magnetic poles trace out a cone in space, and the beams of radiation, channeled along the magnetic field lines, sweep around with them. If Earth happens to lie within the cone traced by one of the beams, we see a pulse each time the beam crosses our line of sight. If we're outside the cone, the neutron star is invisible to us, at least in terms of pulsed radiation. The radiation can be emitted across a wide range of wavelengths, from radio waves to gamma rays, depending on the neutron star's properties. Most pulsars are detected in radio, where the beams are brightest and easiest to observe with large radio telescopes. But some pulsars emit primarily in X-rays or gamma rays, requiring space-based observatories to detect. The exact mechanism that generates the radiation is still debated. It involves charged particles accelerating along magnetic field lines, emitting photons as they spiral and collide. But the details are complex and not fully resolved. Rotation rates vary widely. The slowest known pulsars rotate once every few seconds. The fastest, known as millisecond pulsars, rotate hundreds of times per second. The current record holder, PSR J17482446 AD, completes 716 rotations every second. At that speed, a point on the star's equator is moving at roughly a quarter of the speed of light. The star is flattened slightly by centrifugal force, but gravity is strong enough to hold it together. Any faster and the star might begin to shed material from its equator, though even millisecond pulsars are comfortably below that limit. Millisecond pulsars are thought to be old neutron stars that have been spun up by accreting matter from a companion star. When a neutron star is born, it typically rotates a few times per second, perhaps faster if the original core was rotating rapidly. Over time, magnetic braking slows the rotation. The magnetic field interacts with charged particles in the surrounding space, and this interaction transfers rotational energy away from the star, gradually increasing the rotation period. Left alone, a neutron star would slow down over millions of years until it rotates so slowly that it no longer produces observable pulses. But if the neutron star is in a binary system, and if matter from the companion star falls onto the neutron star, the process changes. The infalling matter carries angular momentum, and as it spirals inward and crashes onto the star's surface, it transfers that momentum to the neutron star, spinning it back up. This process, called recycling, can take a neutron star that has slowed to a rotation period of seconds and spin it up to millisecond periods. The result is a millisecond pulsar, an old neutron star that has been rejuvenated by its companion. Pulsar timing, the precise measurement of when pulses arrive, has become a powerful tool in astrophysics. Because the pulses are so regular, any deviation from the expected arrival time can reveal information about the pulsar or its environment. If the pulsar is in a binary system, the orbital motion causes the arrival times to vary in a predictable pattern, allowing astronomers to measure the orbit with extraordinary precision. If the pulsar has planets, which a few do, the gravitational pull of those planets causes tiny shifts in the timing. Pulsar timing has even been used to test general relativity, measuring the decay of orbits due to gravitational wave emission. One of the most famous examples is the Hulse-Taylor binary, a system containing two neutron stars orbiting each other. Observations of the pulsar's timing over decades have shown that the orbit is decaying at exactly the rate predicted by general relativity, as the system loses energy to gravitational waves. This was the first indirect evidence for gravitational waves, decades before they were directly detected by LIDAR. The precision of the measurement, matching theory to better than 1%, earned Russell Hulse and Joseph Taylor the Nobel Prize in Physics in 1993. Not all neutron stars are pulsars, at least not in the sense that we can detect them. The beams of radiation are directional, and if they don't point toward Earth, we don't see them. Estimates suggest that we only detect about 10% of the pulsars in the galaxy, the ones whose beams happen to sweep across our location. The rest exist, spinning and emitting, but invisible to our telescopes. This means that the total population of neutron stars is much larger than the number of pulsars we've catalogued. Some neutron stars, particularly older ones, may have slowed down so much that they no longer produce detectable radio emission. Their magnetic fields weaken over time, and the processes that generate the beams become less efficient. These are sometimes called dead pulsars, though they're not truly dead, just quiet. They still exist, still spin, but they no longer light up our detectors. Finding them requires other methods, such as detecting their X-ray emission from residual heat, or observing their gravitational effects on nearby objects. Pulsars also exhibit occasional irregularities. Glitches, sudden increases in rotation rate, occur when the superfluid interior of the neutron star couples to the crust, transferring angular momentum and briefly speeding up the observed rotation. These events are rare, unpredictable, and provide a window into the interior structure of the star. After a glitch, the pulsar gradually returns to its pre-glitch slowdown rate. But the brief disruption offers clues about the behavior of superfluid matter under rotation. The discovery of pulsars transformed our understanding of neutron stars. Before pulsars were found, neutron stars were purely theoretical, predicted by physics but never observed. Pulsars made them real, gave them observable signatures, allowed us to study them in detail, and the timing precision they offer has turned neutron stars into some of the most useful objects in astronomy. Tools for testing fundamental physics, mapping the galaxy, and exploring the universe in ways that would be impossible otherwise. They are clocks, lighthouses, laboratories, all in one. Small, dense, spinning remnants of dead stars that continue, long after their violent birth, to illuminate the cosmos with steady, rhythmic pulses. And in those pulses, we find not just signals, but answers, slowly accumulating, pulse by pulse, year by year, as we listen to the quiet, persistent ticking of objects that refuse to fade into darkness. Neutron stars possess magnetic fields far stronger than anything else in the known universe. A typical neutron star might have a magnetic field of around 1 trillion Gauss, which is trillions of times stronger than Earth's magnetic field. This alone is extraordinary. But there's a subset of neutron stars whose fields are stronger still, by factors of hundreds or thousands. These are magnetars, objects whose magnetic fields reach 1,000 trillion Gauss or more, strong enough to distort the quantum vacuum, to rip atoms apart from 1,000 kilometers away, to fundamentally alter the physics of space around them. The magnetic field of a neutron star originates from the field of the original star, compressed and amplified during the collapse. When the core shrinks from a radius of thousands of kilometers to just 10 or 20, the magnetic field lines are squeezed together, and the field strength increases dramatically. The exact amplification depends on the details of the collapse, the rotation of the core, and the behavior of the conducting plasma during those first chaotic moments. But the result is clear. Neutron stars are born with intense magnetic fields, and some are born with fields far more intense than others. Magnetars are thought to form when something unusual happens during or shortly after the neutron star's birth. The exact mechanism isn't certain, but the leading idea involves a dynamo process in the first few seconds of the neutron star's existence. If the core is rotating rapidly and convecting vigorously, the motion of charged particles can amplify the magnetic field through a feedback loop, similar to how Earth's magnetic field is generated, but far more powerful. The result is a field strong enough to dominate the star's behavior for thousands of years. These fields are not static. They evolve, they twist, they decay over time. The magnetic field threads through the neutron star's crust and extends into space, shaping the environment around the star. In magnetars, the field is so strong that it exerts physical stress on the crust itself. The crust, though incredibly strong, is also brittle, and the magnetic forces can strain it, twist it, crack it. When the crust fractures, the energy stored in the magnetic field is suddenly released, and the magnetar emits a burst of X-rays or gamma rays. These bursts can be brief, lasting a fraction of a second, or they can be sustained, glowing for hours or days. The energy released in a single burst can exceed the total energy output of the Sun over an entire year. The bursts are unpredictable, irregular, and they make magnetars some of the most variable objects in the sky. Unlike pulsars, which emit steady, rhythmic pulses, magnetars flare, brighten, dim, and change on timescales ranging from milliseconds to months. The strongest burst ever recorded from a magnetar occurred in December of 2004, when an object catalogued as SGR 180620 emitted a giant flare. For a tenth of a second, the flare was brighter in gamma rays than any other object in the sky, except the Sun. The burst was so intense that it measurably affected Earth's ionosphere, despite the magnetar being nearly 50,000 light-years away on the opposite side of the galaxy. The energy released in that brief flash was more than the Sun emits in 250,000 years. Yet, even that enormous release was just a tiny fraction of the energy stored in the magnetar's magnetic field. The total magnetic energy of a magnetar is staggering, enough to power such flares repeatedly over thousands of years. But the field is gradually decaying, twisting and dissipating, and as it does, the magnetar slowly quiets. Over tens of thousands of years, a magnetar's field weakens to the point where it resembles an ordinary neutron star, and the bursts cease. What's left is a slowly rotating, cooling neutron star, indistinguishable from others except perhaps for subtle differences in its magnetic field geometry or rotation period. Magnetic fields also shape how neutron stars emit radiation. In pulsars, the field channels particles along the magnetic poles, creating the beams that we observe as pulses. In magnetars, the field is so strong that it dominates the emission, producing X-rays and gamma rays not from particle acceleration, but from the decay of the field itself and from the heating of the crust by magnetic stresses. The spectrum of light from a magnetar is different from that of a typical pulsar, shifted toward higher energies, more variable, less predictable. The field also affects the surrounding space. At distances close to the magnetar, the magnetic field is strong enough to affect the quantum vacuum, causing a phenomenon called vacuum birefringence. In this regime, the vacuum itself behaves like a polarizing medium, splitting light into different polarizing states depending on the direction of the magnetic field. This effect, predicted by quantum electrodynamics, has been tentatively observed in the light from at least one magnetar, providing a rare test of physics in conditions we can't replicate on Earth. Farther from the star, the magnetic field extends into a magnetosphere, a region filled with charged particles trapped and accelerated by the field. These particles spiral along field lines, emitting radiation as they move. The magnetosphere of a magnetar is more energetic and chaotic than that of an ordinary pulsar, and it can extend thousands of kilometers into space. The interaction between the field and the surrounding environment, whether it's residual gas from the supernova or matter from a companion star, creates complex and dynamic structures that evolve over time. Not all magnetars are isolated. Some are found in supernova remnants, still surrounded by the debris of the explosion that created them. The interaction between the magnetar's field and the expanding shell of gas can power the remnant, causing it to glow more brightly than it otherwise would. Other magnetars are found in binary systems, though this is rare. The intense magnetic field can affect the companion star, stripping away its outer layers or distorting its shape. Magnetars are rare. We've identified only a few dozen in our galaxy, compared to thousands of ordinary pulsars. This rarity might be because magnetars are short-lived, at least in their active phase. If the intense magnetic activity lasts only a few tens of thousands of years, and neutron stars live for billions of years, then at any given time, only a small fraction of neutron stars would be magnetars. The rest would have evolved past that phase, their fields decayed, their crusts settled. Or it might be that only certain neutron stars become magnetars, those born with the right conditions, the right rotation rate, the right internal dynamics. If so, magnetars represent a specific evolutionary path, a branch in the family tree of neutron stars that only some follow. Either way, they offer a window into extreme physics, into magnetic fields that reach the limits of what the universe allows, into conditions where the usual rules bend and break. The study of magnetars is still relatively young. The first confirmed magnetar was identified in the late 1990s, and the field has grown steadily since then. Each new observation, each burst, each flare adds to the picture. We've learned that magnetars are more diverse than initially thought, that their behavior varies widely, that their fields evolve in complex ways. We've learned that magnetic energy, not just rotational energy, can power neutron star emission. And we've learned that the universe contains objects whose magnetic fields are so strong that they challenge the boundaries of known physics. They are, in a sense, natural laboratories for studying magnetism in regimes we could never create ourselves. And they remind us that neutron stars, despite their small size, despite their quietness after the violence of their birth, are still among the most extreme, most powerful, most strange objects we've ever encountered. The surface of a neutron star is the flattest, naturally occurring surface in the universe. Gravity is so strong that any irregularity, any mountain or valley, is pulled flat within moments. The tallest features, if they exist at all, are no more than a few millimeters high. For scale, if you could somehow shrink Earth to the size of a neutron star while keeping its surface features proportional, Mount Everest would be reduced to a bump smaller than the thickness of a human hair. On a neutron star, even that would be too large. The surface is smooth to a degree that's difficult to fully appreciate. This smoothness is a consequence of the immense gravitational field. At the surface, gravity is around 200 billion times stronger than on Earth. Any material that tries to pile up, any structure that tries to rise above the average surface level, is crushed back down. The crust itself, though extraordinarily strong, cannot support any significant relief. The neutron star's surface is defined by the outer edge of the solid crust, a crystalline lattice of atomic nuclei and electrons, compressed into a structure unlike anything found elsewhere in nature. Above the crust lies the atmosphere, though calling it that is almost generous. It's a layer of gas, ionized by the intense heat and radiation that extends only a few centimeters from the surface. In those few centimeters, the density drops from the solid crust to nearly zero. The atmosphere is made primarily of hydrogen or perhaps carbon, depending on the neutron star's history and composition. If the star has been accreting material from a companion, the atmosphere might be hydrogen-rich. If it's an isolated neutron star, cooling for millions of years with no external input, the atmosphere might consist of heavier elements like carbon or even iron. Despite its thinness, the atmosphere plays a crucial role in shaping the spectrum of light we observe. Radiation from the hot interior escapes through the surface and passes through the atmosphere, where it interacts with the atoms and ions. The intense gravity compresses the atmosphere to such high densities that the gas is nearly as dense as a liquid, and the interactions between photons and matter are strong. The emerging spectrum carries the signature of these interactions, and by studying it, astronomers can infer the temperature, composition, and even the strength of the magnetic field at the surface. The temperature of a neutron star's surface varies depending on its age and history. Young neutron stars, fresh from the supernova, can have surface temperatures exceeding 10 million degrees. At these temperatures, the surface glows brightly in X-rays, easily detectable by space-based observatories. Older neutron stars, having radiated away much of their initial heat, cool to temperatures of around a few 100,000 degrees, still extraordinarily hot by any normal measure, but much fainter and harder to detect. Cooling happens slowly. A neutron star radiates heat from its surface in the form of photons, primarily X-rays and ultraviolet light. At the same time, neutrinos escape from the interior, carrying energy away more efficiently than photons in the early stages. Over the first million years, neutrino cooling dominates, and the interior temperature drops rapidly. After that, photon cooling from the surface becomes the primary mechanism, and the temperature declines more slowly. By the time a neutron star is 1 billion years old, its surface might have cooled to just a few tens of thousands of degrees, and it becomes nearly invisible, detectable only through its gravitational effects or by chance observations. The surface is not uniform. Magnetic fields which thread through the crust and extend into space create hotspots at the magnetic poles. Charged particles, channeled along the field lines, crash into the surface near the poles, heating those regions to higher temperatures than the rest of the star. These hotspots are small, perhaps just a few kilometers across, but they glow brightly in X-rays, and as the neutron star rotates, they come in and out of view, creating pulsations in the observed brightness. The rotation of the neutron star also affects the surface in subtle ways. Centrifugal force from the spin causes a slight equatorial bulge, though the effect is minor given the strength of gravity. More interesting is the effect of frame dragging, a prediction of general relativity where the rotation of a massive object drags space-time around with it. Near the surface of a rapidly rotating neutron star, space-time itself is rotating, and particles or light moving near the star are swept along. This effect, though small, has been measured in at least one system, providing another test of Einstein's theory in an extreme environment. The crust, just below the atmosphere, is solid but not static. It can crack and shift, particularly in magnetars where the magnetic field exerts enormous stress. When the crust fractures, the release of energy produces bursts of radiation and can also cause glitches, sudden changes in the neutron star's rotation rate. The exact strength of the crust, how much stress it can withstand before breaking, is an open question that depends on the detailed arrangement of nuclei in the lattice and the role of impurities or defects. The surface also interacts with the environment. If the neutron star is moving through the interstellar medium, it creates a bow shock as it plows through the thin gas, similar to the wake of a boat moving through water. The bow shock heats the gas, causing it to glow, and in some cases, this emission is detectable, providing clues about the neutron star's motion and the density of the surrounding medium. Some isolated neutron stars have been discovered this way. Their surface is too cool to detect directly, but their bow shock's bright enough to stand out. In binary systems, the surface can be bombarded by material falling from a companion star. This accretion heats the surface to temperatures far higher than a cooling, isolated neutron star would reach. The infalling material, mostly hydrogen and helium, crashes into the surface at a significant fraction of the speed of light, releasing energy in a flash of X-rays. In some systems, the material builds up on the surface until the pressure and temperature are high enough to trigger nuclear fusion, producing a thermonuclear explosion that brightens the neutron star suddenly and dramatically. These events, called X-ray bursts, can be seen across thousands of light years. The surface of a neutron star is in many ways a boundary between the extreme interior and the relatively normal space beyond. It's where the matter of the crust meets the thin atmosphere, where the intense gravity shapes everything, where radiation escapes and carries information outward. It's smooth, hot, and impossibly dense, a surface unlike any other in the cosmos. We can't visit it, can't land on it, can barely even imagine standing near it. But we can observe it, indirectly through the light it emits, and the way that light changes. And in those observations, we find details about temperature, composition, magnetic fields, rotation, all the properties that define the neutron star and reveal the physics of matter in its most compressed, most extreme state. The surface is where the neutron star reveals itself to the universe, where the hidden interior sends its signals outward, where we, from thousands of light years away, can look and learn and slowly piece together the nature of something small, dense, and endlessly strange. Not all neutron stars drift alone through the galaxy. Many exist in binary systems, orbiting companion stars in a gravitational dance that can last for millions or even billions of years. These systems are diverse, ranging from tight orbits where the two objects circle each other in hours, to wide orbits measured in years or decades. The companion can be another neutron star, a white dwarf, a normal star, or, in rare cases, each type of system offers a different window into the physics of neutron stars and their interactions with their environment. When a neutron star orbits a normal star, particularly one that has evolved off the main sequence and expanded into a giant, the gravitational pull of the neutron star can strip matter from the outer layers of the companion. This process, called Roche-Lobe overflow, happens when the companion expands enough that its outer atmosphere crosses the boundary where the neutron star's gravity becomes dominant. The gas, no longer bound to the companion, flows toward the neutron star, spiraling inward under the influence of gravity and angular momentum. This stolen material doesn't fall straight onto the neutron star. The rotation of the system, combined with the conservation of angular momentum, causes the gas to form an accretion disk, a flat, swirling structure that orbits the neutron star before gradually spiraling inward. The disk can extend thousands of kilometers from the neutron star's surface, though it's typically only a few meters thick. Within this disk, particles collide and rub against each other, losing energy through friction, and as they lose energy, they drift slowly closer to the star. The process is continuous, gentle from a distance, though the physics at work is anything but calm. As the material in the accretion disk spirals inward, it accelerates and heats up. By the time it reaches the inner regions of the disk, just kilometers from the neutron star's surface, temperatures can exceed millions of degrees. At these temperatures, the gas emits X-rays, high-energy radiation that streams outward into space. These X-ray emissions make binary neutron star systems some of the brightest objects in the X-ray sky, visible to space-based telescopes across vast distances. The X-rays are not constant. They flicker and vary as clumps of material move through the disk, creating patterns that astronomers can study to understand the dynamics of the system. Sometimes, material accumulates on the surface of the neutron star itself. The gas from the accretion disk settles onto the star's crust, forming a thin layer that grows gradually over time. Under the intense gravity and pressure near the surface, this layer becomes denser and hotter. When enough material has built up, the conditions become extreme enough to trigger nuclear fusion. The hydrogen or helium in the layer ignites all at once, releasing a tremendous burst of energy in a process called a thermonuclear X-ray burst. These bursts are brief, lasting anywhere from a few seconds to several minutes, and they can outshine the entire steady X-ray emission of the system by a factor of thousands. X-ray bursts are remarkably regular in some systems, occurring every few hours or days with almost clockwork precision. In others, they are erratic and unpredictable. The reasons for this variability are not entirely understood. The rate at which material accumulates, the composition of the accreted gas, the temperature and magnetic field of the neutron star, all of these factors influence when and how a burst occurs. Astronomers observe these bursts to study the conditions on neutron star surfaces, to measure their masses and radii, and to test theories of nuclear physics under extreme conditions. But each new observation tends to reveal more complexity than expected. In some binary systems, the accretion process doesn't just heat the neutron star, it can also spin it up. Neutron stars are born rotating quickly, but over time they slow down as they lose rotational energy. However, when a neutron star accretes matter from a companion, the infalling material carries angular momentum. As this material settles onto the star's surface, it transfers that momentum, causing the neutron star to spin faster. Over millions of years, an old, slowly rotating neutron star can be spun up to rotation periods of just milliseconds. These objects are called millisecond pulsars, or sometimes recycled pulsars, because the accretion process has effectively revived their rapid rotation. Millisecond pulsars are among the most stable rotators in the universe. Their pulses arrive with such regularity that they can rival or even exceed the precision of atomic clocks. This stability makes them valuable tools for testing fundamental physics, including theories of gravity and space-time. But their existence also points to the long, complex lives that neutron stars can lead. A neutron star born alone may simply slow down over billions of years, gradually fading from view. One born in a binary system, or one that later captures a companion, may experience multiple phases: pulsar, accretion, rebirth as a millisecond pulsar, and eventually quiescence again if the companion is consumed or lost. Not all binary companions are normal stars. Some neutron stars orbit white dwarfs, the dense remnants of stars, like our Sun. In these systems, the neutron star may pull material from the white dwarf in much the same way, forming an accretion disk and emitting X-rays. Other neutron stars orbit other neutron stars, forming double neutron star binaries. These systems are quieter, with no ongoing accretion, but they are dynamically fascinating. The two objects orbit each other, bound by gravity, slowly losing energy as they emit gravitational waves. Over enormous spans of time, their orbit decays, and they spiral closer together. Eventually, they merge. We'll return to that. Then there are systems where a neutron star orbits a massive, normal star that hasn't yet died. These are called high-mass X-ray binaries. The companion star is often a blue supergiant or another type of massive star with a strong stellar wind. The neutron star plows through this wind, capturing material and forming a temporary accretion flow. The X-ray emission in these systems can be highly variable, pulsing as the neutron star rotates and the density of the wind changes. Some of these systems show eclipses, where the companion star passes in front of the neutron star, temporarily blocking the X-rays. These eclipses provide valuable information about the size and structure of both objects. Binary systems also reveal the effects of neutron star magnetism. In some cases, the neutron star's magnetic field is strong enough to channel the inflowing material onto specific regions of the star's surface, near the magnetic poles. This creates hotspots that emit X-rays in focused beams. As the neutron star rotates, these beams sweep across space, and if one points toward Earth, we see regular X-ray pulses. These are called accretion-powered pulsars, distinct from the rotation-powered pulsars that emit beams from their magnetic poles without any accretion. The pulse periods in accretion-powered pulsars can change over time as the star spins up or down, depending on the torque applied by the magnetic field and the accretion flow. There are odder systems still. Some neutron stars are in highly elliptical orbits, swinging close to their companions and then retreating to great distances. Others are in orbits so tight that the two objects would fit inside our Sun. A few systems show evidence of a third body, a distant companion orbiting the binary pair, creating a gravitational environment of extraordinary complexity. Each configuration teaches us something different about how these systems form, how they evolve, and how gravity and magnetism shape the space between stars. One particularly strange class of binary involves a neutron star and a companion that may be a black hole. These systems are rare and difficult to confirm because black holes don't emit light on their own. The evidence comes from the dynamics of the orbit and the mass of the unseen companion. If the companion is too massive to be a neutron star or white dwarf, it's likely a black hole. In these systems, the neutron star is the one donating material, pulled apart by tidal forces as it orbits ever closer to the black hole. Eventually, it will be consumed. The final moments of such a system are among the most extreme events in the universe, though we have yet to observe one directly. Binary neutron star systems are laboratories for physics we cannot replicate on Earth. They allow us to study accretion, magnetic fields, nuclear burning, gravitational dynamics, and the behavior of matter under pressures and densities that exceed anything achievable in a laboratory. They also remind us that neutron stars are not static objects. They interact, evolve, exchange material and energy, and sometimes they collide. Those collisions open a different chapter entirely. But even without collisions, binary systems raise quiet mysteries. Why do some systems produce regular X-ray bursts while others do not? What determines whether a neutron star will spin up or spin down during accretion? How do magnetic fields evolve in these systems? And what role do they play in controlling the flow of material? We observe the light, the pulses, the bursts, and we build models to explain them. But the models are approximations, and the systems are far more complex than any equation can fully capture. Each new observation adds a piece to the puzzle, but the puzzle itself grows larger with every piece we place. When two neutron stars orbit each other, they do not orbit forever. The system loses energy, gradually and invisibly, in the form of gravitational waves, ripples in the fabric of space-time itself, propagating outward at the speed of light. This energy loss is extraordinarily slow at first, undetectable on human timescales, but it accumulates over millions or billions of years. As the system loses energy, the orbit shrinks. The two neutron stars draw closer together, orbiting faster and faster in a slow spiral that will end in collision. Gravitational waves were predicted by Einstein's theory of general relativity over a century ago, but they were not directly detected until 2015, when two black holes merged and sent a pulse of space-time distortion through the cosmos. The detectors that recorded that event, known as LIGO, are among the most sensitive instruments ever built, capable of measuring changes in distance smaller than a fraction of a proton's width. In the years following that first detection, LIGO and its partner observatories have recorded dozens of mergers, including several involving neutron stars. The most famous of these occurred on August 17, 2017, and it changed the way we study the universe. On that day, gravitational wave detectors in the United States and Italy recorded a signal lasting about 30 seconds. The signal's frequency increased steadily over that time, a telltale sign of two objects spiraling inward, their orbit tightening in the final moments before merger. The characteristics of the signal, its amplitude, frequency evolution, and duration, revealed the masses of the two objects. Both were consistent with neutron stars, each roughly 1.5 times the mass of the Sun. Within seconds of the gravitational wave detection, observatories around the world received another alert. A gamma-ray burst had been detected from the same region of sky, arriving just under 2 seconds after the gravitational wave signal ended. This was the first time a cosmic event had been observed in both gravitational waves and electromagnetic radiation. It was the beginning of what astronomers call multi-messenger astronomy. Over the following hours and days, telescopes across the electromagnetic spectrum turned toward the source. Optical telescopes found a bright new point of light in a galaxy about 130 million light-years away, in the constellation Hydra. Infrared telescopes tracked the glow as it evolved and faded. X-ray and radio observatories watched for delayed emission from material ejected during the collision. The observations continued for weeks, then months, building a detailed picture of what happens when two neutron stars merge. It was one of the most intensely studied events in the history of astronomy, and it revealed phenomena that had only been theorized before. The collision itself was brief and catastrophic. As the two neutron stars spiraled inward, tidal forces began to distort their shapes. Neutron stars are incredibly rigid, but even they deform under the immense gravitational pull of a nearby companion. The deformation increases the energy loss, accelerating the in-spiral. In the final milliseconds, the two stars were orbiting each other hundreds of times per second, separated by only a few dozen kilometers. Then they touched. The outer layers of the stars collided first, compressed and heated to billions of degrees in an instant. A fraction of this material was flung outward at a significant fraction of the speed of light, expanding into space as a cloud of neutron-rich matter. What remained at the center depended on the total mass of the system. In some mergers, the combined mass exceeds the maximum possible mass for a neutron star, and the core collapses immediately into a black hole. In others, the remnant forms a hypermassive neutron star, temporarily supported by rapid rotation, but unstable. This object may survive for seconds or minutes before it too collapses into a black hole. In rare cases, if the total mass is low enough, a stable neutron star may form. The fate of the August 2017 merger is still debated, though most evidence suggests a black hole formed within seconds of the collision. The material ejected during the merger is where much of the story's richness lies. This material, unbound from the gravitational pull of the core, expands outward and begins to decay. Neutron-rich nuclei, unstable and heavy, undergo rapid radioactive decay, releasing energy in the form of heat and light. The expanding cloud glows, first blue, then red, as it cools and the elements within it settle into more stable configurations. This glow is called a kilonova, and it's far brighter than a classical nova, but not as bright as a supernova. The kilonova from the 2017 event was visible for weeks, fading slowly as the ejected material cooled and dispersed. Within that ejected material were elements that cannot be easily formed anywhere else. When neutron-rich nuclei decay, they build up heavier and heavier elements through a process called rapid neutron capture, or the R process. This process creates many of the heaviest elements in the periodic table, elements like gold, platinum, uranium, and thorium. Before the observation of the 2017 kilonova, the origin of these elements was uncertain. Supernovae were thought to be a possible source, but models struggled to produce enough of the heaviest elements. The kilonova provided strong evidence that neutron star mergers are a primary, perhaps the primary, source of R process elements in the universe. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in a nuclear reactor, much of it likely formed in the violent merger of two neutron stars, billions of years ago, long before the Sun or Earth existed. The gamma-ray burst that accompanied the merger was brief, lasting only about 2 seconds, but it was intensely energetic. Gamma-ray bursts are among the most luminous events in the universe, and they come in two types, long and short. Long bursts, lasting more than 2 seconds, are associated with the collapse of massive stars. Short bursts, lasting less than 2 seconds, have long been suspected to come from neutron star mergers, and the 2017 event confirmed this. The burst was directed along the spin axis of the system, forming a narrow jet of radiation that happened to be pointed roughly, though not exactly, toward Earth. If the jet had been aimed directly at us, the burst would have been far brighter. If it had been aimed away, we might not have detected it at all. Not every neutron star merger produces a gamma-ray burst. The jet must form, and it must be oriented in our direction. Some mergers may produce no detectable electromagnetic counterpart at all, visible only in gravitational waves. Others may produce different signals depending on the masses of the stars, the strength of their magnetic fields, and the amount of material ejected. Each merger is unique, and astronomers are only beginning to understand the full range of possible outcomes. Gravitational wave detectors continue to operate, and more neutron star mergers have been detected since 2017, though none have had such a clear and bright electromagnetic counterpart. Each new detection adds to our understanding of how common these events are, how neutron stars are distributed in mass, and what happens in the moments after collision. The next generation of gravitational wave detectors, planned for the coming decades, will be even more sensitive, capable of detecting mergers across most of the observable universe. We will see these events regularly, perhaps daily, and with each one we will refine our picture of neutron star physics, nuclear matter, and the origin of the elements. But questions remain. What determines whether a hypermassive neutron star forms or whether collapse to a black hole is immediate? How much material is ejected, and what controls the composition and velocity of that ejector? How do magnetic fields influence the dynamics of the merger and the formation of jets? How long can a hypermassive remnant survive, and what signals does it emit before it collapses? The 2017 event answered many questions, but it opened just as many more. The collision of neutron stars is no longer a purely theoretical event. It is something we have witnessed, studied, and begun to understand. But understanding, in science, is always provisional, always incomplete. there is always more to see. The story of how we came to know about neutron stars begins not with theory, but with an unexpected signal. In the summer of 1967, a young graduate student named Jocelyn Bell was working at a radio observatory in Cambridge, England, analysing data from a newly constructed telescope. The telescope was designed to study quasars, distant and luminous objects at the edges of the universe, but it was sensitive enough to pick up other signals as well. Bell's job was to sift through miles of paper chart recordings, looking for anything unusual. One day, she noticed something strange: a series of sharp, regular pulses, each separated by exactly 1.337 seconds. The signal was so regular, so precise, that it seemed almost artificial. At first, the possibility that the signal was extraterrestrial in origin was considered, half seriously. The source was even jokingly labelled LGM-1 for Little Green Men. But as Bell and her advisor, Anthony Hewish, continued their observations, they found more pulsing sources in different parts of the sky. The signals were natural, not artificial, but their origin was unclear. No known astronomical object pulsed with such regularity. Stars flickered and varied, but not like this. The pulses were sharp, consistent, and arrived with a precision that suggested something rotating, something small and dense, sending out beams of radiation like a lighthouse. The explanation came quickly once the data was clear. Theoretical physicists had predicted decades earlier that neutron stars should exist. The collapsed cores of massive stars held up by neutron degeneracy pressure. These objects would be incredibly dense and would rotate rapidly, conserving the angular momentum of their progenitor stars. If a neutron star had a strong magnetic field, and if that field was misaligned with the rotation axis, it could produce beams of radiation from its magnetic poles. As the star rotated, the beams would sweep across space, and if Earth happened to lie in the path of one of those beams, we would see a pulse. The pulsing sources were neutron stars, and they became known as pulsars. Jocelyn Bell had discovered the first direct evidence of neutron stars, objects that had been theoretical until that moment. The discovery earned the Nobel Prize in Physics in 1974, though controversially, the prize was awarded to Anthony Hewish and the radio astronomer Martin Ryle, not to Bell. Her contribution was eventually recognized more widely, and she has since become one of the most respected figures in astronomy. But the discovery itself opened a new field of study, one that continues to this day. Since 1967, more than 3,000 pulsars have been discovered. They are found through radio surveys, systematic scans of the sky that listen for periodic signals. The process is painstaking. Radio telescopes collect data across wide regions of sky and across a range of frequencies. Software analyzes the data, searching for repeating patterns. Most signals are noise, interference from Earth, random bursts from space, but occasionally a clear, steady pulse emerges. Each new pulsar is catalogued, its period measured, its position recorded. Over time, patterns have emerged. Most pulsars have periods between 1/10 of a second and a few seconds. Some are much slower, some much faster. The fastest known pulsar rotates 716 times per second. The slowest rotate once every few seconds. Pulsars are observed not just in radio, but across the electromagnetic spectrum. Some emit pulses in visible light, though these are faint and difficult to detect. Others pulse in X-rays, particularly those in binary systems accreting matter from a companion. A few emit gamma rays, high-energy photons, that require space-based telescopes to observe. Each wavelength reveals different aspects of the pulsar's behavior and environment. Radio observations tell us about rotation and magnetic fields. X-ray observations reveal accretion and surface processes. Gamma-ray observations probe high-energy particle acceleration near the neutron star's magnetic poles. Gravitational wave detectors, like LIGO, add another layer. While most gravitational wave detections come from mergers, there is also the possibility of detecting continuous gravitational waves from a single, rapidly rotating neutron star. If it has a slight asymmetry, a mountain or a bump on its surface. Such signals would be far weaker than merger signals, and none have been confirmed yet, but searches are ongoing. If detected, they would provide information about the neutron star's shape and internal structure. Despite these tools, neutron stars are difficult to study. They are small, distant, and emit most of their energy in forms that are absorbed by Earth's atmosphere. Radio signals can penetrate the atmosphere, but they are faint and require large, sensitive telescopes. X-ray and gamma-ray telescopes must be placed in space, and they are expensive and limited in number. Gravitational wave detectors are incredibly sensitive, but they only detect transient events or very specific continuous sources. Most neutron stars in the galaxy are invisible to us, either because they are not oriented to beam radiation in our direction, or because they have cooled and slowed to the point where they no longer emit detectable signals. We estimate that there are around 100 million neutron stars in our galaxy, based on the rate of supernova explosions and the fraction of stars massive enough to form neutron stars. But we have detected only a few thousand. The vast majority are silent, at least from our perspective. They drift through the galaxy, dark and undetectable, remnants of ancient explosions that no longer announce their presence. Some may be isolated, far from other stars. Others may be in binary systems we haven't noticed. A few may be nearby, closer than any known pulsar, but simply not pulsing in a direction we can see. The variety of signals emitted by neutron stars is remarkable. Some pulsars are extraordinarily stable, their pulses arriving with clockwork precision over years or decades. Others show glitches, sudden increases in rotation rate caused by shifts in the neutron star's interior. Still others emit giant pulses, sporadic bursts of radio emission, thousands of times brighter than their regular pulses. Some pulsars pulse in a regular pattern, while others show nulling, intervals where the pulses disappear entirely for minutes or hours before resuming. We don't fully understand why these variations occur. Each behavior points to complex physics, interactions between the magnetosphere, the crust, and the interior that we are only beginning to model. Observations continue. New radio telescopes, more sensitive and with wider fields of view, are discovering pulsars at an increasing rate. Space-based X-ray and gamma-ray observatories are refining their instruments, detecting fainter sources and studying known neutron stars in greater detail. Gravitational wave detectors are being upgraded, preparing for the next generation of sensitivity. Each new instrument, each new survey, brings the possibility of discovering something unexpected, a new class of neutron star, a new emission mechanism, a signal that doesn't fit existing models. That possibility keeps the field alive. Jocelyn Bell's discovery, made on strips of paper chart recordings in a cold English summer, revealed a universe stranger and richer than anyone had imagined. The regular pulses, so precise they seemed artificial, were the heartbeat of a dead star, smaller than a city, denser than an atomic nucleus, spinning hundreds of times per second and beaming radiation into the darkness. We have been listening to those pulses for more than 50 years now, and they still have more to teach us. Neutron stars are not a single uniform category. They vary in rotation rate, magnetic field strength, temperature, age, and environment. And these differences produce a wide range of observable behaviors. Over decades of observation, astronomers have identified several distinct classes, each defined by how the neutron star emits energy and how it interacts with its surroundings. The boundaries between these classes are not always sharp. Some neutron stars seem to belong to more than one category, or transition from one to another over time. The classification is useful, but it's also provisional, a way of organizing what we see, rather than a reflection of fundamental divisions in nature. The most common class is the rotation-powered pulsar. These are neutron stars that emit beams of radiation powered by their rotational energy. As the star spins, its magnetic field accelerates charged particles near the magnetic poles, and those particles emit radiation, primarily in radio wavelengths. Each time the star rotates, the beam sweeps across space, and if it crosses Earth, we detect a pulse. Over time, the pulsar slows down as it loses rotational energy. Young pulsars, born in supernova explosions within the last few thousand or million years, tend to rotate faster and emit more energy. Old pulsars, billions of years old, rotate more slowly and are fainter, sometimes fading below detectability. Then there are millisecond pulsars, neutron stars that rotate extraordinarily fast, hundreds of times per second. These are often old neutron stars that have been spun up by accreting matter from a companion star in a binary system. The process can take millions of years, but the result is a neutron star rotating far faster than it did at birth. Millisecond pulsars are remarkably stable. Their pulse arrival times can be predicted with such precision that they are used as cosmic clocks, tools for testing general relativity and searching for low-frequency gravitational waves. Some millisecond pulsars are still in binary systems, orbiting white dwarfs or other companions. Others are isolated, their companions long since consumed or lost to space. Magnetars are another distinct class, defined by their extraordinarily strong magnetic fields. While typical neutron stars have surface magnetic fields 1 trillion times stronger than Earth's, magnetars have fields 10 to 1,000 times stronger still. These fields are so intense that they dominate the star's behavior, twisting and stressing the crust, generating bursts of X-rays and gamma rays when the crust cracks and magnetic field lines reconnect. Magnetars rotate more slowly than typical pulsars, often with periods of several seconds, and they emit most of their energy in X-rays rather than radio waves. They are rare, only a few dozen are known, and they tend to be young, born within the last few tens of thousands of years. Over time, their magnetic fields decay and their activity decreases. An old magnetar may become indistinguishable from a normal, slowly rotating neutron star. There are also X-ray pulsars, neutron stars in binary systems that accrete matter from a companion and emit pulsed X-rays as the accreted material is funneled onto the magnetic poles. These are sometimes called accretion-powered pulsars to distinguish them from rotation-powered pulsars. Their pulse periods can be quite different from rotation-powered pulsars, ranging from milliseconds to minutes, and the periods often change over time as the accretion torque spins the star up or down. Some X-ray pulsars show periodic outbursts, brightening dramatically for weeks or months before fading again. These outbursts are linked to variations in the rate of accretion, which in turn depends on the orbit and the state of the companion star. Central compact objects are a quieter class. These are neutron stars found near the centers of supernova remnants, the expanding clouds of gas left behind by the explosion that created them. They emit X-rays, powered by residual heat from their formation, but they don't pulse, or, if they do, the pulses are too faint or too irregular to detect easily. They rotate slowly, and their magnetic fields appear weaker than those of typical pulsars. They are young. Most are only a few thousand years old, and they may represent a different evolutionary path. Neutron stars born with weaker fields or in explosions that left them spinning more slowly. Their properties are still being studied. Isolated neutron stars, sometimes called Magnificent Seven, are another small group. These are nearby neutron stars within a few hundred light-years of Earth that emit thermal X-rays from their surfaces but show little or no pulsar activity. They are warm, not freshly born, but not ancient either, perhaps hundreds of thousands of years old. They rotate slowly, with periods of several seconds, and their spectra suggest surface temperatures of around 1,000,000 degrees. They appear to have relatively weak magnetic fields and no companions. They are quiet, cooling embers, visible only because they are close and because space-based X-ray telescopes are sensitive enough to detect their faint glow. Some neutron stars don't fit neatly into any category. There are rotating radio transients, neutron stars that emit sporadic, unpredictable bursts of radio emission separated by minutes or hours of silence. There are intermittent pulsars which pulse steadily for days or weeks and then turn off completely, only to resume later. There are sources that emit in X-rays, but not in radio, or vice versa. There are neutron stars with unusual pulse profiles, emission that doesn't match standard pulsar models. Each anomaly suggests that the physics of neutron stars is more complex than our classifications imply. Neutron stars evolve. A young pulsar, born rotating rapidly, slows down over millions of years as it radiates away rotational energy. If it's isolated, it will eventually fade from view, becoming a dim, slowly rotating neutron star, emitting little detectable radiation. If it's in a binary system, it may accrete matter and spin up, becoming a millisecond pulsar. If the companion is another neutron star, the system will eventually merge, forming either a more massive neutron star or a black hole. If the magnetic field is exceptionally strong, the neutron star may spend some time as a magnetar before the field decays. The path any given neutron star takes depends on its initial mass, rotation, magnetic field, and whether it has a companion. No two neutron stars are exactly alike. The boundaries between classes are not firm. A magnetar might also be an X-ray pulsar. A millisecond pulsar might also be in a binary system accreting material. A central compact object might eventually be identified as a slow, weak pulsar once better observations are made. The categories are descriptive, not rigid. They reflect what we observe, and what we observe is limited by the sensitivity of our instruments and the direction in which the neutron star's radiation is aimed. There are likely many more classes we haven't recognized yet, because we haven't seen enough examples or because the defining characteristics are too subtle to detect with current technology. What is clear is that neutron stars are more diverse than early models suggested. They are not simply inert remnants, static and unchanging. They rotate, pulse, flare, accrete, cool, spin up, spin down, crack, reconnect, and emit across the electromagnetic spectrum. They exist in binaries and in isolation. They are young and old, hot and cool, fast and slow, radio loud and radio quiet. Each one carries information about its birth, its history, and the physical laws governing matter at extremes. Each one is a small, dense archive of processes we are only beginning to read. Even after more than 50 years of observation, neutron stars remain among the least understood objects in the universe. We know what they are, broadly: collapsed stellar cores held up by neutron degeneracy pressure, and we have mapped their basic properties. But the details, the deeper questions about their interiors, their fields, their emissions, and their numbers remain largely unanswered. The more closely we look, the more questions emerge. This is not a failure of science. It is the natural state of inquiry, especially when studying objects we cannot touch, cannot recreate, and can barely observe. One of the most fundamental mysteries is what happens at the center of a neutron star. We know the outer layers are composed mostly of neutrons, with a crust of atomic nuclei and a thin atmosphere. But as you descend toward the core, densities rise beyond anything we can achieve in laboratories. At some point, neutrons themselves may break down into their constituent quarks, forming a state of matter called quark matter. Alternatively, the core might contain exotic particles, like hyperons or condensates of mesons. Or it might remain neutrons all the way through, just compressed to the point where the interactions between them become impossibly complex. Different equations of state, different models of nuclear physics, predict different core compositions. Observations of neutron star masses and radii can constrain these models, but they cannot yet definitively distinguish between them. The core remains hidden, inaccessible, a region where the laws of physics are pushed to their limits. Magnetic fields present another enduring puzzle. We know that neutron stars have intense magnetic fields, and we know that some, the magnetars, have fields far stronger than typical pulsars, but we don't fully understand how these fields are generated or why they vary so widely. The fields are likely remnants of the magnetic field in the progenitor star, amplified during the collapse when the core shrinks and field lines are compressed. But the exact mechanisms of amplification, the role of rotation and convection during collapse, and the processes that can produce a magnetar strength field remain uncertain. We also don't know why magnetic fields decay. Observations suggest that magnetar fields weaken over time. But the timescale and the physics behind the decay are not clear. Some neutron stars seem to have much weaker fields than expected. Whether they were born that way or whether their fields have decayed is unknown. Pulsar emission mechanisms are better understood now than in 1967, but gaps remain. We know that pulsars emit beams of radiation from near their magnetic poles, and we know that the radiation is produced by accelerated charged particles. But the exact location where the emission originates, the processes that accelerate the particles, and the reasons why some pulsars emit in radio while others emit in X-rays or gamma rays are still debated. Different models predict different emission zones. Some place the radio emission close to the neutron star's surface, others far out in the magnetosphere. Observations support both, in different cases. The pulsar magnetosphere is a complex dynamic environment, and our models are approximations. Each new observation refines them, but a complete, unified theory of pulsar emission does not yet exist. Some pulsars behave in ways that don't fit any model. They emit giant pulses, sporadic bursts of radio emission far brighter than their regular pulses. For reasons we don't understand, they show nulling, intervals where emission stops entirely, and mode switching, where the pulse profile changes suddenly. They glitch, abruptly spinning faster due to shifts in the interior, and then slowly relax back toward their previous rotation rate. Each of these phenomena points to physics we haven't fully captured, interactions between the solid crust and the superfluid interior, instabilities in the magnetosphere, or processes we haven't even considered yet. The regularity of pulsars, the feature that made them detectable in the first place, is punctuated by irregularities we are still working to explain. We also don't know how many neutron stars exist. Estimates suggest around 100 million in our galaxy, based on the supernova rate and stellar evolution models. But those estimates are uncertain. We've detected only a few thousand. The rest are invisible, either because they aren't pulsing in our direction, because they've cooled and slowed below detectability, or because they're too distant for current instruments to see. There may be a large population of old, cold neutron stars drifting silently through the galaxy, detectable only if they happen to pass very close to Earth, or if future infrared telescopes can spot their faint, thermal glow. Some may be nearby, within a few light years, and we simply don't know they're there. Binary systems add layers of complexity. Why do some neutron star binaries produce regular X-ray bursts while others do not? What determines the spin evolution of an accreting neutron star? Whether it spins up or spins down? How do magnetic fields interact with accretion flows? And what role do they play in launching jets during mergers? How long can a hypermassive neutron star formed in a merger survive before collapsing into a black hole? Each question has partial answers, but the full picture remains unclear. Binary evolution is complex, involving mass transfer, tidal interactions, magnetic torques, and orbital dynamics, all coupled together in ways that are difficult to model precisely. Gravitational wave observations have opened new questions. We've now detected a handful of neutron star mergers, but each one raises as many mysteries as it resolves. How much material is ejected during a merger? And what controls the velocity and composition of that ejector? How common are these events, and how much do they contribute to the total mass of heavy elements in the universe? Can we use gravitational wave signals to measure the equation of state of neutron star matter? And if so, how precise can those measurements be? The answers will come from more detections, better models, and closer collaboration between gravitational wave astronomers and nuclear physicists. But we're still in the early stages. There are also questions we haven't thought to ask yet. Neutron stars may exhibit behaviors we've never observed, emit signals we haven't looked for, or interact with their environments in ways we haven't considered. Every major advance in observational capability has revealed new phenomena. Radio telescopes revealed pulsars. X-ray satellites revealed accretion and bursts. Gravitational wave detectors revealed mergers and kilonovae. The next generation of instruments, more sensitive gravitational wave detectors, larger radio arrays, advanced X-ray observatories, will undoubtedly reveal more. Some discoveries will fit into existing frameworks. Others will require entirely new physics. This is the state of neutron star science, rich in data, full of models, and perpetually incomplete. We have learned an extraordinary amount since Jocelyn Bell noticed those regular pulses in 1967. We understand that neutron stars are dense, magnetic, rapidly rotating remnants of massive stars. We have measured their masses and radii, mapped their emission across wavelengths, detected their collisions, and traced their evolution through multiple phases. But we have not solved them. The core composition is uncertain. The magnetic field origin is unclear. The emission mechanisms are debated. The population is mostly invisible. The behaviors are often unpredictable. This incompleteness is not a flaw. It is the nature of studying the universe. Neutron stars are laboratories for physics at extremes. Densities where atomic nuclei merge into a fluid of neutrons. Magnetic fields that warp space-time. Rotation rates that approach the speed of light at the surface. Temperatures in the millions of degrees sustained for millennia. We cannot recreate these conditions. We can only observe from afar, build models, test predictions, and refine our understanding slowly, over decades and generations. Each answered question opens new ones. Each new observation challenges old assumptions, and so the work continues, patient and persistent. Radio telescopes scan the sky, listening for faint, regular pulses. X-ray satellites monitor known neutron stars, watching for bursts and flares. Gravitational wave detectors wait for the signal of merging remnants. Theorists refine equations of state, model magnetospheres, simulate supernovae in collisions. Observers and theorists compare notes, adjust models, propose new observations. The process is slow, incremental, and ongoing. Understanding grows not in sudden leaps, but in the gradual accumulation of data and insight. The slow construction of a coherent picture from thousands of small pieces. Neutron stars will remain mysterious for a long time. They are small, distant, and governed by physics we are only beginning to understand. But they are also real, observable, and endlessly fascinating. Each pulse that arrives at a radio telescope, each X-ray burst detected from orbit, each gravitational wave signal recorded by LIGO carries information about matter, gravity, magnetism, rotation, collapse, and merger. We collect that information piece by piece, and we build our understanding slowly. The work is far from finished, and perhaps it never will be. But that is what makes it worth doing. The universe is full of wonders we have yet to see, questions we have yet to ask, and neutron stars, dense, magnetic, spinning remnants of dead stars, remain among the most profound.